I actually only have one example for you today, so maybe we should change this to sample calculation, but it does have multiple parts, so maybe we're okay. And it's just a simple LR circuit with a single inductor and a single resistor and a battery, and we want to answer all kinds of questions about it. The first question is, what is the current at t equals 0? Well, if we close the switch at t equals 0, for an instant we have to remain at 0 current. If not, if we were at non-zero current, we would have jumped from 0 current to non-zero current in no time, and that would mean that di dt is infinite, and we can't have that because then our inductor here would have had an infinite voltage, and anyway, those things aren't going to happen. So whenever we've got an inductor in the current, we can't have infinite rates of change, so that means the initial current has to be 0 for an instant. Alright, that one was nice and easy. What is the time constant? This one is also pretty simple. If you remember, our time constant is given by the inductance over the resistance. So we've got 220 millihenries over 30 ohm resistor. So since I left this in millihenries, that just means my time constant is going to come out in milliseconds. It comes out to be approximately 7.3 milliseconds. Guess I should have boxed that guy up. It was an answer after all. Part C, what is the maximum current? So the inductor slows the rate of change, but in the long run it doesn't affect the circuit overall. After a while, when the current reaches a steady state, it's like the inductor's not there at all. So if we ignore that inductor, we can just find the maximum current by using Ohm's law, V over R. We've got our voltage of 12, our resistance of 30, and we get a 0.4 amp maximum current. Moving right along, part D, how long will it take the current to reach half of its maximum? So here we got to use one of our new fancy equations. We can say that the current is V over R. Now this V over R was the maximum current, and we've also got this 1 minus e to the negative t over tau thing going on. So if we're going to reach half of our maximum, essentially this part in parentheses here is going to be equal to 50%, or 0.5. So we can forget about the rest of the equation and just solve this little guy right here. We're going to get e is negative t over tau is equal to a half. We do natural log of both sides, so we get negative t over tau is equal to the natural log of 1/2. Multiply the tau up over here. That negative sign is going to go away because whenever you have a natural log of something less than 1, you're going to get a negative there. We go ahead and plug in 7.3, but convert it to regular seconds, and you'll get 0.00508. I guess we didn't have to convert it. We could have had 5.08 milliseconds, but anyway, this is how long it takes. Just about off the bottom of the screen there, sorry. Alright, part E. At this instant, what is the rate of energy being delivered by the battery? So rate of energy is a fancy way of saying power. And power is I times V. Now you have to be careful what V you're plugging in here. If you're finding the power dissipated by the resistor or the inductor or the battery, you would need to plug in the voltage drop across whichever of those you're interested in. For us, it's the battery, so we're just going to plug in 12, and the current is half of its maximum. We know the maximum is 4, so half of the maximum, not 4, 0.4, so half the maximum is just 0.2, so we multiply that by 12, and we get 2.4 watts. Okay. Part F, what is the rate that energy is being stored in the magnetic field? Now, if we think about this 2.4 watts of power that the battery is delivering, the battery power goes two places. Part of it goes to the inductor, and part of it goes to the resistor. Oops, I meant P sub R. So this is actually much simpler to just find the power through the resistor and then subtract that from the power from the battery to get the power in the inductor, and that's what we'll do first. So the power in the resistor is going to be I squared R rather than finding the voltage drop. We already know I and we already know R, so we might as well use that version of our power equation. So we're going to have 0.2 squared times 30, and this works out to be 1.2 watts. Now the total is 2.4. 1.2 goes to the resistor. We subtract that from the total and we get the power for the inductor is essentially the other half, 1.2 watts. Now if we want to find the power of the inductor directly, it will be a bit more work. Hopefully I've got room here. So we know the energy in an inductor is 1/2 Li squared, but we're interested in the rate of change of energy. So we want du dt, and so that's going to be the derivative of this whole thing, 1/2 Li squared. Now we can pull out the 1/2 and the L because those are constant with time. So we're going to have the derivative of I squared, and that just works out to be 2I, but then by chain rule we're going to have a di dt left over here. 2 goes and cancels with the 1/2. I'm going to jump back over here, and we have IL di dt, where I switch the I and the L to be suggestive here because L di dt is the EMF of the inductor. I'll put E sub L. And we can use a Kirchhoff voltage rule. I think I said current rule earlier in the previous video when I should have said voltage loop. But anyway, we know that that is going to equal the battery voltage minus the voltage drop across the resistor, right? Because you'd have this minus this guy equals 0, so you can move that to the other side. And so here we get our expression, right? This guy here is going to give us the power dissipated, because that's du dt for our inductor. And we know these values, so we can go ahead and plug in. I'm going to jump over here. The current, once again, was 0.2. That V is the battery voltage, 12. The current, again, times the resistance. And guess what? It is consistent. We get 1.2 watts. All right. Have a nice day.